So the first model we want to talk about is our model for simple interest. So our simple interest model is I is equal to P times R times T. So I is our total interest. P is our principal, or our starting amount. R is our interest rate. And lowercase t is going to be time. So our simple interest model is I equals P times R times T, where a capital I is our interest, P is our starting amount, R is our interest rate, and T is time. We're going to use this model to help us solve our first example. So Martine has $4,000 invested in two different accounts. A low-risk account pays 2% simple interest, and a high-risk account pays 8% simple interest. If he made $230 in interest last year, our goal is to find out, well, how much money is in each account. So whenever we're trying to use a model, we need to figure out what it is we're trying to find, so what is our unknown, and we need to assign it a variable. So we're supposed to find out, well, how much money is in each account. So let's let X be the amount invested in the low-risk account. So then we can use that to help us find the amount in the high-risk account. So we know that the total in both accounts is $4,000. So then the amount in the high-risk account is 4,000 minus X. So let's talk about why it's 4,000 minus X for a minute. Well, this is another example of what we were talking about last time. If we're ever not sure what to do with a variable, we can just pretend that that variable is a number. So if Martine put $1,000 in the low-risk account, and we know he had $4,000, then he had to put 4,000 minus 1,000 in the high-risk account. So remember, the variable will always do whatever a number would do if it was it. So if you're unsure what we were going to do with 4,000 and X, whether it was add, subtract, divide, or multiply, just pretend it's a number and see what you would do, and then we would follow the same pattern. The way I prefer to work these types of problems is I like to organize my data into a table. So to help me do so, I write my model, and I give myself a little space in my model, because each variable in my model represents a column in my table. So I'm going to have 1, 2, 3, 4 columns, and then I'm going to get a row for each of my accounts and this. So I have my low risk account, I have my high risk account, and then I'm going to have some information about the totals. So now I need to fill in this table. So Martine has $4,000 invested in two different accounts. So that's not the amount in the low risk, it's not the amount in the high risk, but it is the total. So that means the 4,000 is going to go here in my table. The next piece of data we run into is our low risk account has a 2% interest, so that's our R, but before we can use R, we always have to convert our percents to a decimal by moving our decimal 2 places to the left. And then we have our high risk account, which pays 8%. So as a decimal, that's going to be our high risk and its interest rate, so 0.08. And then if he made $230 in interest last year, well, that's not from the low risk, it's not from the high risk, that is the total, so that's going to go down here. How much money is in each account? Well, there's a couple more pieces of information. One of them is our variable. So we said let X be the amount invested in the low risk account. Well, that's our P column. So our low risk is X, and our high risk is going to be 4,000 minus X. But there's one more piece of information that's kind of hidden in here, and it's hidden in words, and that is last year. So last year is going to be the amount of time, and that's going to be, last year would be 1 year. So then that gives us the values that we end up with in our table. And our model tells us that our interest I right here is equal to P times R times T. Well, in our first row, we notice that P is X, our interest rate is 0.02, and our T is 1. So this has to be the same as P times R times T, or X times 0.02 times 1 gives us 0.02X. And this is just the product of these three things multiplied together. Similarly, we're going to do the same thing here. We're going to multiply these three things together. So 1 times 0.08 times 4,000 minus X is 0.08 times 4,000 take away X. Well, that fills in our first column. So we know then this expression, 0.02x, represents the interest in the low risk account. The expression 0.08 times 4,000 minus x represents the interest in the high risk account. So if I add those two things together, it has to be the total. So then our final equation is 0.02x plus 0.08 times 4,000 minus x is equal to $230. And that gives us our linear equation, that first column, that we need to resolve to solve for x. So to solve this equation, first thing we do is we open our parentheses by distributing the 0.08 into our parentheses. So we have 0.02x plus 0.08 times 4,000 is 320. 0.08 times negative x is negative 0.08x is equal to $230. So now, to solve, we need to gather up our like terms. So we have a 0.02x and a negative 0.08x, which gives us negative 0.06x plus 320 equals 230. We minus 320, and we minus 320, giving us negative 0.06x is equal to negative 90. And we divide by negative 0.06 and divide by negative 0.06, and that gives us that x is equal to we have negative 90 over negative 0.06, and we get $1,500. So we get x is 1,500. So now we go back to our variable declaration at the very beginning, and what was X? X was the amount invested in the low-risk account. So the low-risk account had $1,500. Then the high-risk account has $4,000 minus $1,500. So the low-risk account has, I guess this was in the past, had $1,500, and the high-risk account had 4,000 minus this, so 4,000 minus 1,500, which is $2,500. So the amount in the low risk account was 1,500, and the amount in the high risk account was 2,500. So in general, for these types of problems, the most difficult aspect is actually setting up the equation. Once we get the equation, it's pretty straightforward from there. So let's kind of recap what happened here. And I'm a big fan of these. We'll use it again in the next example. I like making tables to help me organize my data and come up with the equations. They're not necessary. You can do them without the table, but I find this to be a very helpful tool in keeping everything organized. So when we do that, we put our model across the top and our accounts down the side, and then just fill in the information and use that to help us figure out what we know and what we're trying to find. And always make sure to make a clear declaration of what we are looking for. All right, so let's move on to our next example. But before we do, we're going to need another model. So the next model that we're going to be using is, I like to call it the freeway model, which is if you get on the freeway and drive 60 miles an hour for 5 hours, how far did you go? Well, 60 times 5 is 300 miles. Well, that's exactly the formula that we're going to use. So our next model is our distance model, which is different from the distance formula that we talked about in Chapter 1, Section 1. So our model is d, so our distance is equal to rate times time. So d is our distance, r stands for rate, but what that really means is our speed, and our t is going to be time. So distance is equal to rate times time. And we're going to use this to help us solve our next example. So example 2 says, a suspect in a high-speed chase enters I-8 eastbound at 60 miles per hour. 12 minutes later, a highway patrolman enters I-8 eastbound at the same location at 75 miles per hour. How long until the officer catches up with the suspect? Okay, so we're going to do the same thing. So how long until the officer catches up with the suspect? So let's let x be the amount of time the officer or the patrolman is on the freeway. All right, so we make our chart. We have D equals R times T. And we're going to have our patrolman and our suspect. So let's see what we know. Well, we know that our suspect was going 60 miles per hour, and 12 minutes later a highway patrolman enters I-8 eastbound at the same location going 75 miles per hour. Well, here's where we have to be a little bit careful. So 12 minutes later, a highway patrolman enters I-8 eastbound. So then who has been on the freeway longer? Well, that would be the suspect. So we know that X represents when the highway patrolman got on the freeway. The suspects have been on there for 12 minutes longer. So it's going to be X plus 12. And that plus 12 comes from the fact that 12 minutes later, the highway patrolman got on. So now we have the same thing happening that happened in our previous chart. D is equal to R times T. So the distance traveled by the highway patrolman is 75 times X. And the distance traveled by the suspect is going to be 60 times X plus 12. So now, for the patrolman to catch the suspect, they have to be in the same place. That means that the distances that they traveled must be the same. So the distances must be equal. So that's really our key idea here. So then that would give us the equation 75x is equal to 60 times x plus 12. So now we need to solve this equation for the time. So once again, we open our parentheses by distributing, and we get 75x is equal to 60x plus 60 times 12 gives us 720. We minus 60x and we minus 60x, and that gives us 15x is equal to 720. And we divide by 15, we divide by 15, and that gives us x is equal to 48. So at those speeds, it would take 48 minutes. All right. So once again, a little bit of a recap. We used our model, which was distance is equal to rate times time. Remember, when we make our tables, for each variable in our model, we get a column, and then we put our information as the rows, fill in what we know, and then we had to use this key idea here, that if you're trying to catch someone, you must be in the same place at the same time. So the distance that they traveled must be the same. So the distances must have been equal. We set them equal to each other, and we solve. All right. So next thing we're going to do is transition away from these applications to something a little bit different. And we want to talk about zeros, solutions, and X-intercepts. So if we think back to an earlier section when we were talking about X-intercepts, to find the X-intercept, what did we do? We set y equal to 0 and then solved for x. So keep that in mind as we proceed through this next definition. So a 0 of a function is an input that we're going to name C such that the output for C is equal to 0. So notice in our definition of a 0, it doesn't say we're putting 0 in, right? A 0 of a function is an input, so some number that when we put it in, the output is 0. So when we say 0, we're talking about the output, not the input. And as we talked about, this is the same as the ordered pair. And remember, our ordered pairs are always input and then output. It is the ordered pair C, comma, 0. So we're trying to find any number that when we put it in, we get 0 out. Oh, well, this is exactly the same thing as the X-Intercept. In fact, it's worth noting, note zeros, solutions, and X-intercepts are the same thing. So we're going to expand on that for a minute, but this tends to be a point of confusion because mathematicians are going to bounce around between zero solutions and X-intercepts, and we will use these words as if they are synonyms, because they are. Each of them comes preloaded with a little bit of context, as we'll see. So when we say zeros, we know we're specifically talking about a function. When we're talking about X-intercepts, we're talking about a graph. And when we're talking about solutions, we're talking about it in its equation form. But in reality, all three of these are exactly the same thing. If you know one of them, you know all of them. So don't let that bother you. So it's really easy to think we're talking about three different things. We're not. They're all the same thing. It's just we'll use them when we're talking about things in different contexts, but they're exactly the same point when we're talking about them on a graph. Example 3 will help illustrate this point. So let's take a look at example number 3. Alright, so for example number 3, we're asked to find the zeros and the x-intercept of the function. So if I were to look at my graph, well, the x-intercept is where my graph crosses the x-axis. Well, that's going to be right here. This is my x-intercept. And its ordered pair is going to be the point 4, 0. Well, if I write this in function notation, it says if I input 4, my corresponding output is 0. So then the 0 is x equals 4, which is exactly this. So our zeros and our x-intercepts are exactly the same. It's just two different ways to talk about the same point. One of them is the ordered pair on the graph, and the other one is in the function notation in terms of the input. So our 0 is the input, which is 4, that when I put it in, my output is equal to 0. So when we say a 0, we're really talking about the output. All right, so now it is your turn. I want you guys to find the 0 on this graph. So we identify our x-intercept as this point right here. And that's going to have ordered pair 2, 0. So then our function notation would be f of 2 equals 0. So our 0 is x is equal to 2. So that would be our x-intercept and the 0 of that function. All right, so let's keep building on this idea. Oh, that is not what I meant to click. All right. So we want to find the 0 of this linear function. So the idea is the same as what we've been doing, but we also said that a 0, a solution, and x-intercepts are the same thing. Well, we find that by setting f of x equals to 0. So the solution to f of x equals 0 is the 0. So in this case, if we have f of x equals 0, our f of x is 2 over 5x minus 6 is equal to 0. Notice this is exactly the same way we would find the x-intercepts. You set y equal to 0 and you solve, because y and f of x are the same thing. We add 6, and we get 2/5 x is equal to 6. We multiply by 5, we multiply by 5. Those reduce out, and we get 2x equals 30. Divide by 2, divide by 2. So our x value is 15. So the 0 is x equals to 15. So, some food for thought. Well then, what is f of 15? Well, if I plug that back into the original equation, that's 2 over 5 times 15 minus 6. Well, 5 goes into 15 3 times. 2 times 3 is 6, and 6 minus 6 equals, 0. As advertised, right? Because we solved for the input, then when we put it in, what should we get out? 0, because that's what it means to be a 0. All right. All right, so to find the 0, we set f of x equal to 0, which is 3 minus 2x equals 0. So we add 2x, and we add 2x. And that gives us 3 equals 2x, and we divide by 2, so we get x is 3 halves. So then our 0, in this case, is going to be 3 over 2, And if we plug that back in, we could check that indeed that would be the solution to our linear equation. So one thing I do want to mention is if we grab our graphing device, let's go ahead and put this function in, so clear out what we have in here. And if I put 3 minus 2x into my calculator, and I press graph, there's a couple of things we're going to want to take note of. So first thing, when you press graph, you're probably not going to see anything because we've been messing with our window. So one thing we want to know how to do on our graphing calculator is if we press our zoom key, which is in the middle in the top row of keys, and then choose choice number 6 for standard, that'll take us back to the standard 10 by 10 window on our graphing calculator. And the other thing is we probably have some dots. You probably can't see yours now, but we have our scatter plot on our graph. That's not desirable. So when we're done doing that, to turn off our scatter plot, what we do is we go second, and we go to y equals, and we're going to go down to choice number 4, which is plots off, and then press enter. So remember, to turn the plots on, we went second y equals, and we went down to choice number 5 and chose plots on. When we don't want our scatter plot to show up anymore, we do the same thing. We go second y equals, but instead of plots on, we choose plots off. And press enter, and it'll say done. And now when I graph, I get something that looks like this without my scatter plot on it. So now that we're back to our regular graph, it turns out that our calculator can help us find that point. So what I want everyone to press on your calculator is the second key and then trace, and it's going to open up our calculate menu. And what is it that we're trying to find? The zeros. Well, the 0 is choice number 2. So we select choice number 2 from our menu, and then our calculator is going to ask us 3 questions. It says left bound, and when we're talking about the bounds, we're talking about x values. So we need to make sure that our cursor's x value is to the left of the 0, which it is. And then it says right bound, so I use my right arrow till my x value is to the right of the 0. And remember, zeros are the same as x-intercepts, which is where our graph crosses the x-axis, so I press enter. And then lastly, it says guess. So then just move your cursor as close as you can to the x-intercept and you press enter. And what does my calculator tell me? It says my 0 is located at x equals 1.5. And as we know, it turns out 1.5 and 3/2 are the same thing.